Okay, welcome to Unit 10. This is the last unit, and it's going to be chapters 28, 29, 30, and a little bit of 31. And so it's all about magnetism, magnetic fields, and the way that magnetism relates to electricity. So we're going to be looking at circuits, we're going to be looking at forces on charged particles, and all kinds of things like that. So, things you already know about magnetism. There's a north and a south pole. In reality, we've only found things that have north and south together. If you cut a magnet in half, you don't get just north and just south, then it redistributes north-south. That would be a monopole. If you had something that was just north, it would be a monopole. And those are theoretically possible in things like string theory, but they haven't been discovered in reality yet. Opposite poles repel, or opposite poles attract like poles repel. And so that should bring up an interesting question. If you hold up a magnet, in the Earth's magnetic field, what direction will the north side point? It'll point to what we call magnetic north, but then that's actually south, right? The Earth's south pole is what we call the North Pole, because that's the pole that attracts the north side of a magnet, right? So keep that in mind. And so magnetic fields, it's a field vector. It points, and it goes around the magnet, and they look, the field lines look like electric field lines. We're not going to get into drawing them as much as we did with electric fields, because we're not going to get into like the number of charged particles and stuff like that. And we measure the magnetic field in Teslas, which is a totally new unit if you haven't studied magnetism. I thought it was kind of funny. I was going for my MRI at one point, and it says, caution, 3 Tesla magnet. And I'm looking at that thinking to myself, oh yeah, people are going to look at that and be like, oh, 3 Tesla. I need to be careful around this thing. Permanent magnets have a permanent magnetic field. Electromagnets can be magnetized if you run an electric current across them. The North Pole is the end from which the field lines emerge. The South Pole is the place where the field lines go to. Monopoles, we talked about. Crossed fields, that's where you have an electric field and a magnetic field perpendicular to each other. Like, for example, light. Light is an electromagnetic wave. The electric field and the magnetic fields are perpendicular to each other. Okay, other important things. Right, field lines work the same as they have before. The density of the field lines tells you the magnitude of the field. However, differences between electric and magnetic fields. The force on a charged particle does not depend on the field lines there alone. It also depends on the velocity. There's only a force on a charged particle from a magnetic field if the particle is moving. And we'll see that in the equation, right? F equals QV cross B. Well, it's coming up. And so, an electric field produces a force on a charged particle whether it's moving or not. So that's a difference. Also, the direction, the electric field produces a force on the charged particle in the direction of the field line, right? Tangent to the field line. The magnetic field produces a force on the particle perpendicular to the velocity of the particle. And so since it's producing a force perpendicular to the direction of the velocity, the magnetic field technically does no work, right? Because work is a dot product. Perpendicular vectors give you a magnitude of 0. So our main unit that we're going to use is a Tesla. And a Tesla is 1 Newton per amp meter. So 1 Tesla is 1 NAM, N over AM. You can see that a Weber is a joule per area, so it's how much energy there is through a certain area, or rather joules per amps. So it's how much energy there is per amount of current, and that's over area. A Weber we'll talk about later, and it's Weber, not Weber. A Weber. And 1 Gauss is 1/10,000th of a Tesla. So sometimes it's good to use Gauss instead of Tesla. Like the Earth's magnetic field is half a Gauss, so it's a smaller number. But it doesn't make a huge difference. Tesla is the main thing we're gonna do here because we can express that in terms of the other SI units, newtons, amps, and meters. So the first equation we have is F equals QV cross B. So it's a cross product. And don't forget the order here matters. When you're figuring out the direction of the force, you put your fingers first in the direction of the velocity, and then you cross in the direction of the magnetic field. And then the direction your thumb is pointing, that's the direction of the force on that particle, right? And the magnitude can be calculated as QVB sine theta. And so in the first, in those pictures there, you can see there's a magnetic field pointing to the right, and then the velocity is either to the right or to the left. There the force is 0 because the movement, the velocity, is parallel to the magnetic field. However, in the other one, the magnetic field is pointing to the right, and the velocity is pointing kind of forwards a little bit, right? And so again, you point your finger in the direction of V, and then cross in the direction of B, and the force ends up going up, right? That's that right-hand rule. And then for the other one, same thing, right? It's moving, if you're kind of holding the paper flat like this, the particle is moving towards you, the magnetic field is going to the right, so again that produces an upward force. Okay, and so then question is, at what angle between V and B is the magnetic force at maximum? Hopefully by now you know cross products 90 degrees is going to give us the greatest magnitude when dealing with a cross product.